more or less. As a case, we look at the simplest geometry possible. So we have this one. It's a two-dimensional steady-state problem. The turbulent process flow between two parallel plates, and that's it. So this is, of course, then a one-dimensional problem. If you use turbulence models, you just simulate across from wall to wall here, finding some turbulent velocity profile, and done. Doing a DNS, on the other hand, you have to run this one in 3 dimension, and you have to use a transient code, because turbulence by nature is 3D and it is transient. So even though you have a one-dimensional problem, it's not a cheap solution if you want a DNS. So what do you get? I'll jump a little ahead here. Come back to this later. This is what we get. So what is this? Well, this is a plane, say close to one of the walls. So the flow direction is here. And what you see is just a contour plot, isoplot of the streamwise velocity, but the average is subtracted. So here it is the sort of just the U flocked alone that you are watching. And the solid lines, meaning you have a region where you have a positive U flocked, the velocity is fast. The dashed negative, then the velocity is a little bit slower. So if you average everything here, you will get 0. So remember, this is just one plane very close to one of the walls. And for all the different planes, it will look something similar. Close to the walls, we get these streaky structures, some turbulent orientation. You have some behavior, obviously, that is getting quite long. And these elongated structures can be a pain. Now remember the boundary conditions. What are we going to do here with the boundary conditions? Here is the inlet. And you have to send in a fully developed turbulent flow field, where the turbulent structures changes with space and time. And you can't find it, of course, it's not possible. So what I do here, I use periodic boundary conditions. So I just set up a driving force, and then whatever goes out there, I send in here. Same goes in the spanwise direction. So if you have any structure going out here, you will enter up here, and vice versa. But if you choose a domain that is not long enough, if you look at the longest streaks here, how long can they be? Well, fairly long. This one is so long, and also he continues here. That's sort of getting dangerously long, because if you have one structure that goes through the entire domain, you will have sort of a self-amplification due to the periodic boundary conditions. He will bite himself in the tail. And that's unphysical. So your domain has to be so long that these streaky structures can be contained within your domain. And they will typically be of order 2,000 plus units. So your domain has to be at least then 4,000 plus units.
And when you say you put up a driving force, you need some kind of pressure condition?
Yeah.
Does that one also need to have fluctuations? And
no.
Can you just do a pure?
No, because you take your equation of motion, now the Navier-Stokes, no Reynolds averaged, and there you have a dp dx, where one now might think, okay, that one should now be increased with a constant. What you can do is, of course, to say that the pressure 1 here, P1, is then bigger than the pressure here, P2, because you have cyclic or periodic boundary conditions. But then what you do, you say, you take a equation, and then after the pressure gradient, the viscous term, you say -1. Then you have a constant driving force. Or put a gravity, it doesn't matter, it's just a constant driving force into the problem. That's what you need. So you don't mess around with the real pressure field, because the pressure is also going to look something like this.
Exactly.
So you can't sort of interfere with the variables. No, you have to add a driving force sort of externally. Yeah. So the task will now be to ensure that this one is realistic. And how to do that? So here we have our problem. Send in a flow here and hopefully get a turbulent average velocity profile looking something like this. And here I believe I had the length scale. Here was, what was it, 2h or something. So my length scale in the problem, be h or 2h if you like. And if you want to calculate the Reynolds number, of course you use this as a length scale, and you use the average velocity and the viscosity, and then you have the Reynolds number. Then on the other side you have something called Kolmogorov microscales. A length scale, eta, which describes sort of the smallest length scale you have in a flow. The size of the smallest little turbulent eddy, how big is this one? The smallest scale imaginable. I mean, this one is something that you see on movies. You go to a cheap Norwegian B movie, and then you see they sink a boat or they explode a building or something. And it looks artificial, it doesn't look real. So what they have done is, of course, to make a tiny, small little model and then blow it up. And it looks fake. And what looks fake is the ratio, your length scale, divided by the Kolmogorov length scale. They haven't gotten this ratio right. When you go to a Hollywood movie and very expensive, billion-dollar budget, they blow up real scale models. It looks real. They have gotten this ratio right. So that's the whole difference. Not to destroy the movie experience for you, but to be aware. And it can be shown that this ratio will go as the Reynolds number to the power of 3/4. And for this flow, or say flow between two parallel plates, the Reynolds number, bulk Reynolds number, has to be around 3000 to make it turbulent. Then it's just a turbulence. It's very close to laminar actually. So the number of cells you're going to need from wall to wall will be 3000 to the power of 3/4. It's not such a big number. But remember, the number of cells that we are going to need will be the Reynolds number to the power of 9/4, because we have a three-dimensional flow. And now take 3000 and raise it to the power of 9/4, and you get a very big number. So that is the problem with DNS. You have to resolve the Kolmogorov microscale, or else you haven't captured all the physics in the problem. Also, you have a Kolmogorov time scale, a tau, which then also is very, very small. Meaning your delta t has to be quite small. The DNS that I did was based on finite differences, so I have to worry about the Courant number, I have to worry about the cell Reynolds number, that should be smaller than 2. But I had to use a so small delta t anyway, so it was not a problem. So, but that means you have to do 100,000s of time step for such a simple problem. To get the turbulence correctly developed, organized in space and time. It takes a long, long time. 100,000 time steps, something like that. So the computational demand here is quite substantial. And just increase the Reynolds number. You blow any memory on any computer easily. So what we can do today, you can have 10 to the power of 9 cells. That should be possible on the biggest computers, but expensive. So we are in trouble here. Yeah, a little bit turbulent theory. It doesn't stand in many turbulence books. The classics is Tenkes and Lumley, Introduction to Turbulence. We have something that we call the correlation. And the question then is, if you are standing at one point inside a flow, how is the velocity at this point correlated to neighboring points? And at what distance? So if you're looking at one point in the, say, streamwise direction, how is this velocity correlated to velocities forward? So here they will be highly correlated since you are in one structure, sort of moving. But if you go in the cross-stream direction, all of a sudden you will have a velocity going the other way around. That's totally not correlated at all. So this correlation coefficient, that's something that can describe how long can you go here in space and still have some degree of correlations between the two different points. If you go, let's say, for this image, I would say you have to go a distance something like this before everything should be zero correlated. They don't talk to each other at all. While in the cross-stream direction here, you don't have to go very far before you find a totally different behavior. They don't correlate to each other at all. So this correlation function, it will then be a velocity at a position r multiplied with a velocity at a different position. And then you scale this one typically with the fluctuating velocity squared. And such a function, it will typically go then something like this. You always start with 1. Then you are in the same point. So then, of course, per definition, this will be 1. And in the streamwise direction, it will here go something like this, and finally go all the way down to 0. So you have to go pretty far before you find, now they are not talking to each other anymore. So this one will now be u, meaning velocity in the streamwise direction, while, we don't call it like that. How do we call it? I think in this article we are going to look into, this one is called R, and here it will be 1, 1, when delta R here being delta X. You look at the velocity in the X direction with different distances also in X direction. If you go the other way, meaning you look at one velocity here and then you go in the y direction and see, okay, how does he correlate to a velocity in a delta y direction? You will typically go something like this. Start with 1 and then he will go negative and then finally level off and maybe even make some wavy motions. So this one will now be R1. It's the u velocity I'm looking at, but I go in the y direction. And this one will now be called 1, 1. So these coefficients, these functions, can tell us something about the flow. So here we have some long structures in the x direction. They are correlated, they talk to each other. While in the cross-stream direction, they go negative, so they will be told the opposite at a certain average distance. And then, having these functions, you take the Fourier transform. Now, taking the Fourier transform, it will be taking the different cosine waves on top of this figure and use then the wavelength for these cosine waves to be weight functions. So here, for this 1, 1, I can have one fairly okay cosine wave, maybe go something like this, which then should be the biggest possible weight. They will match fairly decent. When you have twice as many, then no, he will not be that good. And then you just try with different frequencies. And what you end up with then is what we call an energy spectrum. And it will be a function of the wave number, say 1 over length. And an energy spectrum well, that will now depend. For R11, I will have an energy spectra going something like this, and then fall down. And always these will be in a log plot, meaning here you have a very small wave number, meaning you have the longest scale possible, the biggest lengths. So they contain the most energy. So for this correlation here, they will have a lot of energy with a very low wave number. And then the higher the wave number, the smaller the energy. And here they will just stop at Kolmogorov. Then you don't have any more turbulent energy at all. For the other one, I will actually have a peak at a certain frequency. So they will typically go something like this and then fall off. So I will have a maximum energy at a scale where you have this half wavelength distance. we want to make a quick sketch here of the energy spectra for the ocean, as an example. The energy ocean. And then you have different wavelengths here. The biggest length scale you find in the ocean, that will be the planet. And of course, then we don't have any actually flows on this scale. But a little smaller, the biggest scales you find in the ocean, that will be the tidal currents. The Gulf Stream, some length scale of say 100 kilometers, 1,000 kilometers. They will induce energy into the ocean. So the energy spectra then should have a peak. So here we are talking 100 kilometers, maybe even bigger. And then the energy will start to decay. But then you will have the length scale of, say, tidal flows in and out of fjords. So you have, say, a length scale of 1 kilometers, 1,000 meters. They will give another peak, also induce energy into the ocean, and then decay. And then, say, you have waves, 10 meters scale, will give another peak, and then finally all the way down to viscosity. So an energy spectra can sort of tell you a little bit about the physics inside the flow. Now we are going to resolve this numerically. So the aim is to hit this microscale, to resolve it with our mesh, but it's very expensive. But it's nice for us then that the smallest part here is really not that important. So if I take, say, 10 Kolmogorov here, and just forget about this part. They don't contain much energy, so I do a mistake, but it's not a big one. So yes, we can cheat. We can say you don't have to resolve everything all the way down to Kolmogorov. But you should at least go down to 10 times Kolmogorov. Then you have captured absolutely most of the physics in the problem, most of the energy containing vortices. So 10 times Kolmogorov is a decent DNS still, except very close to the walls. Very close to the wall, that's where all the action takes place. That one has to be resolved. You have to get very close to the wall. Kolmogorov will be around y plus of 1. Little smaller maybe. The distance you should have is y plus of 0.1 close to the wall. You really have to resolve that boundary layer. If you remember the law of the wall, the law of the wall, he looks something like this. You will have a laminar velocity profile. Here you have log y plus, and here you have the u plus. So this one is u plus equals y plus, and when you set in the definitions here for the plus, the turbulent length, turbulent velocity, this will be the same as to say u goes as y squared. This is the laminar velocity profile. And then for y plus around 10, you switch from the inner to the log low. So it will be a straight line in this semi-log graph. And this is highly validated with all the experiments. Yes, this is your velocity profile, very close to the walls. within a turbulent boundary layer. So people have sort of the conception that this sublayer here, the viscous sublayer, it's a laminar velocity profile. So they sort of assume, okay, then the turbulence is sort of decaying here, tends towards laminar flow. That's a very big lie. Very, very big lie. Because when you look at the activity here, very close to the wall, within this sublayer in a DNS, the velocity doesn't look like this at all. You will have definitely the most crazy behavior very close to the wall, and then soften it down, and then very crazy to the wall. So the average velocity, okay, fair enough, he will be laminar-like, but the actual activity, it's really here all the activity takes place. You really have to resolve this layer, although on average it will be like a laminar velocity profile, strangely enough. So you have to resolve the walls. But then further out in the free stream, definitely you can have bigger cells. So there you can cheat. 10 Kolmogorov should be a good approach. When you do a DNS, you know everything. At least we think so. So yes, we can calculate whatever we want. We can calculate these correlations. We can plot these energy spectra. And you will have a warning sign when you plot them if they start to go something like this, or even something like this. Then you know something is wrong. Then you haven't resolved all the scales good enough. Then you need more cells. So that's a warning sign if that ever happens. If it happens, what can you do? Then you cheat. You say, I don't have the money to go all the way down to 10 Kolmogorov everywhere in my domain. I switch on a turbulence model inside one single cell. So the turbulent activity within one cell is now to be modeled with a very simple turbulence model. Randall's mixing layer or something like that. Now you're talking large eddy simulation. Then you can have the cutoff maybe somewhere here and say the most energy containing behavior, there I resolve it. I have plenty of cells to describe it. But in this part of the energy spectra, I model it. So that is sort of the philosophy behind DNS and large eddy.
I've heard that it actually can be dangerous to just trust the energy spectra, so that you, in some cases, you would actually get a spectra which looks quite nice, but you still have too poor resolution, and that you rather should look at the 2-point correlation and then see, okay, how many cells are in between.
I would say, I would still put a question mark. You can't say that the energy spectra or the 2-point correlation can be a proof of anything. If they look okay, then at least you have a suspicion that maybe nothing is wrong. Then your simulation is okay. So it's sort of just to validate that it's not wrong. It may be right.
Is it similar to residuals? If they look bad, then it's definitely bad. If they look good,
it might be correct.
Yeah.
So you have to look elsewhere for evidence that your simulation is a-okay. Remember, the energy spectra is just a Fourier transform of the 2-point correlation, so it's actually the same graph, just plotted another way. So easier to read in some regards, but you can have them both side by side. That's okay. Yeah.
If you resolve twice, are you really only interested in like the large scale averaged flow properties? What kinds of errors do you get if you are far from, if you like naively just don't have small enough cells and you're more turbulence model?
Yeah.
What kinds of errors do you get?
Well, for this test problem, you should create this average velocity profile fairly easy. It won't be hard. but I'll show you when you look at the higher order, that's where you run into problems. You start plotting this one, U float square, time averaged. Not so hard. This will be sort of a part of the K in K epsilon. But of course you need ASMRs and to find it. And then you're looking into U float 3. Now you're talking problems. Not to mention number 4 to the power of 4. These are extremely sensible, more and more sensible to arrows. So here you can really tell, have you done a good simulation or not. But we will come back to it. I'll show you some thoughts of it.
These are the small scale fluctuations, right?
Yes,
I mean,
just the turbulent part of the velocities.
yes. Did you naively just do like pixel DNS? There's not
Yeah,
DNS.
yeah.
I mean, then you don't. You just have one view, right?
Mm-hmm.
And that.
In practice, what's going to happen, I mean, you can fire up Solar and run this case, say 10 by 10 by 10 cells. And then you just use a strong driving force, so the Reynolds number becomes 10,000. And then the simulation is going to explode. Of course, it's going to be unstable. So then what you do, you use smaller and smaller time steps. Not that you can resolve this space, no matter what you do, but at least you can have a stable solution. Yes, you can get a stable solution. With 10 by 10 by 10 cells, I'm not sure what's going to happen, you can try. You should get something out of it, but you won't get, of course, the correct energy. Then with 10 by 10 cells, you are here only. You have missed most of the action, so it's not possible to describe this one correctly. So you get something totally crazy.
Will you have a tendency to get too large velocities since you don't dissipate?
No, because remember, you have one constant driving force in the problem, and then what's going to happen then with this force? Okay, it's going to become motion activity. You're going to need some, say, viscous forces to damp out the driving force into the problem, but you don't have velocities enough and viscosity enough to damp it down. So it's going to be very unstable indeed. I don't think you can get any reasonable results whatsoever, even with very, very small delta T. So you will be in trouble. So you might say what you do then in the DNS, when you have your equation of motion, you have pressure, you have, what do you write it? I write it like this, ddxj of viscosity, du dxj, something like that. Just one component. So what you do, you say this one now reads like this. So again, you adjust the viscosity using large eddy turbulent viscosity, and then actually you cheat, you sort of increase the viscosity so that the turbulent scale is not so violent anymore. But at least now you have a number for this function, so you know sort of your cheat can be documented and understood as a turbulent quantity. Just don't, if you multiply him with 1,000, as I said earlier, that's also a turbulence model, it's just a very bad one. Yeah.
The turbulence model for large eddy, normally it's more, Smagorinsky and so on, it's more simple models.
Yeah,
right?
very
Because
simple model.
they just look at the smaller scales.
Yeah.
How, I mean, if you do a really bad LES,
Yeah.
so that you basically apply this simple model to a big part of your energy spectra.
Yeah.
Is there a rule of thumb when it's actually so bad that you get worse results than runs?
No, no rule. So people have been playing around with what they call large eddy simulation, and very large eddy simulation, and very, very large eddy simulation. So we're sort of squeezing the boundaries every time. So
But would they then still use these simple models, or
Yes.
is it okay?
They will still use it. They have been testing it with the turbulent activity within one cell to be described by K-epsilon models, by Rance models, sort of more advanced than turbulent models. Not worth the effort. Didn't pay off at all. So simple models inside here. Yeah, also, why should you use a transport equation inside one single cell? Transport it to where? It's still inside one cell, so it's sort of pointless. So a simple model is good enough, yes. But they have tested it and found it not worth the effort.
But is it? I mean, if you get very core, it's not worth the effort. But how is it comparing to like a pure round simulation?
Yeah, of course, if you are pushing your cells bigger and bigger here and have a large amount of this energy spectra sort of skipped, of course you're going to have a bad answer, a bad simulation. Then maybe our answer will be much better. Especially when you have a geometry like this. It's a one-dimensional problem for crying out loud, so you can have it very accurately with one dimension. So you need to find other quantities, some evidence to prove that I have solved Newton's second law of motion correct. That's what you're looking for, and you need to verify it somehow, or else you have just a nice picture. Like there's one guy, Kuwahara, Japanese guy, that the car industry loved because he was dealing with what he called DNS in those days. And the industry, Japanese industry, gave him so much money that he bought himself, I think he had 3 supercomputers in his home. In the garage, in the basement, and in his home there were always PhD students in and out all the time using these machines. And he then simulated the flow around a car, which has a Reynolds number which is very big when the car is moving with say 80 kilometers per hour or something. The Reynolds number is many millions. It's not possible to achieve a DNS. He still called it a DNS. And the irritating thing was that he got fairly decent results. And people didn't like that. Of course, the industry in Japan, they loved it. And it turned out that he used a third order upwind scheme, which has an additional artificial diffusion, which was acting as a subgrid scale model. So he was actually doing an LAS without being aware of it. So LAS slash DNS can still produce decent results, reasonable results, although you are pushing your limits a little bit too far, the Reynolds number is a little bit too big, and then, even worse I would say, people will also cheat. I said this one has to be 3-dimensional, it has to be transient. People are still doing this 2-dimensional, steady state, and then play around with large eddy models and actually still gets decent results. We don't like that, but they still do. That's a little impolite, I would say. So I think it's more to this problem here than at first glance. But according to theory, 3-dimensional, transient, and resolve all the scales down to at least a decent level. That should be the basic philosophy. So of course the question, what are you aiming for? If you want an engineering result, the answer plus minus 20% accuracy, fair enough. But if you're doing research, you won't get it published unless you can sort of verify that you have a decent resolution in your simulation. That's a little too much. We don't have time. I think I have to spend an hour then tomorrow with turbulence as well before we start playing around with open foam. Yeah, we are missing some of the material here that I wanted to show you. So 1 hour of turbulence tomorrow. Before we stop today, we sort of have a strong force from above, from our system. We have to design a reference group in this course. It has to be in all courses. So I'm going to need a couple of you to voluntarily be a member of such a reference group. So it won't be much work. We meet together and have a chat. How can we make this course a better course? How can we improve it? What was wrong? What was good? What was bad? So that shouldn't take more than 5 minutes and a cup of coffee. But it's mandatory, we have to do it. So can any of you be voluntarily a member of such a group? Yeah, excellent. Then I have to. I need your emails. And then. Okay, but then 1 hour of turbulence tomorrow, and then we start with open foam. And then we stop here.